Um, for our material selection project, we were asked to examine the lock shackle on a padlock in the class of steels. So the padlock's main function is to safely secure an object by passing its lock shackle through an opening. The lock shackle is the U-shaped part of the padlock that you see on top and that actually clicks and locks the padlock. So some applications of the padlock would be to lock a gate door, to lock a chain together, or to lock a locker. There are many other applications and uses as well. So how does the padlock mechanism work? So in the padlock there's a locking mechanism which houses 3 to 7 spring-loaded pins. And when the correct key is inserted into this locking mechanism, the key's notches will align these pins. These aligned pins will allow the locking barrel to rotate and therefore unlock the shackle and unlock the padlock. The lock shackle itself is commonly designed in a U-shape to allow ease of locking for a broad range of items. These U-shapes can come in either larger or smaller U-shapes as seen on the padlock on the right. Similarly, the padlock can also come in straight shackles instead of the traditional U-shape. Steel is the most commonly used material for padlocks due to its high strength. However, different types of steel can be used based on the padlock's desired applications. For example, if a harder shackle is required, hardened steel can be used. Similarly, stainless steel can be used for increased corrosion resistance for the shackles. Brass can also be used for lock shackles for increased weather and corrosion resistance. However, steel will be the main focus of this project's analysis.
So from understanding how a lock, shackle and padlock is designed and will be used, we can go on to the functional requirements, geometrical requirements and constraints. So for functional requirements, it must be able to resist a certain compressive stress without breaking, and it must be able to correctly lock into the main padlock body without bending. And for the geometrical requirements, it must be a solid cylinder, and we've assumed a radius of 0.5 centimeters. For the constraints, we've set up a safety factor of 10, which will be discussed later, as well as a hardness value minimum of 800 Vickers. The maximum cost we're allowing is $20 per kilogram, and the maximum weight of the lock and shackle shall be 100 grams, which gives a shackle weight of 18. This shackle should not deflect more than 0.01 millimeters, which is around 0.1% of its initial diameter, and this is so that it can retain its functionality. So from these functions and constraints, we can then move on to the main objectives. For a lock shackle, its main purpose is to stop anyone breaking in. So what we want is maximum hardness and compressive strength, but we also want to minimize costs as it's for commercial use. So to analyze the minimum allowable compressive strength, we've taken a very average situation with bolt cutters that are 24 inches long with an exerted pressure on the handles of 30 pounds force. Now, to analyze the force at part D, which is the part that's just compressing the lock shackle, we've drawn the free body diagrams that can be seen at the bottom part of the slide, and we've summated the forces at points y to equal 0, the moments about c to equal 0, and the moments about a to equal 0 in order to get forces b and d. We've also assumed that the forces in the x direction are 0. The force d comes out as 10,800 pounds force, which is around 48,000 newtons. And the stress, which is from this using F over A, is 240 megapascals. We've included a safety factor of 10, as this is a very average case, and we want to be able to have this apply to a wide variety of cases that are unforeseen. So to get our MPI, which relates the Young modulus to density, we first use the same assumptions from the last equation, and we get a delta equals FL cubed over 4EBH cubed, and in order to get our Q value, which is the constant of the slope, we rearrange that to find H and sub it into our M value. Now this comes out for Q to be 1.0964, and in order to get the straight line equation, we take the logarithm of both sides, which ends up being log E is equal to 3 log rho plus 3 log Q.
So taking the MPI derivation using the deflection constraint, a Young's modulus versus density attribute plot diagram can be plotted using the CS software. The obtained graph can be seen on screen right now. The MPI line is not visible within the given scale on screen of the graph. This is due to the y-intercept of the MPI being so small in terms of numerical value compared to the graph scale. The small intercept makes the MPI line shift downwards and effectively includes all initially selected steels as acceptable materials given the MPI. However, this MPI eliminates SiFe, soft magnetic metals, alloys, and air-melted magnetic iron. After this initial Ashby plot, further restrictions and limitations of compressive strength, hardness, and cost can be applied to a compressive strength versus price Ashby plot. The compressive strength minimum limit was set to 2400 megapascals based upon the maximum allowable compressive stress on the lock shackle as previously calculated with the consideration of the 10 safety factor. Likewise, the hardness value was limited to a minimum 800 Vickers based upon average steel hardness values. The average retail cost of a commercial padlock is about $4 US, and taking into consideration a suitable profit margin, the cost of production of the average padlock should be about $2 US, and the average mass of the padlock should be about 100 grams. This makes the maximum allowable material price to be $20 US per kilogram, assuming the shackle and padlock are made from similar materials. After the MPI and further restrictions were applied, these were the 6 suitable steels we were left with. They were all tool steels, and they are shown on screen as of now. So from these 6 steel alloys can be compared in terms of our desired characteristics. These desired characteristics are compressive strength, hardness, fracture toughness, and price. The average value for each characteristic was found on the CES software.
So from these characteristics, we made a decision matrix for all the steels with the AISI M41 as a baseline, and we gave each steel a +1 if it exceeded its relative characteristic, and a -1 if it was worse than the relative characteristic. So from this, we can see that both the AISI M41 and AISI M46 have a total value of 0, which means we will further analyze these. So after this decision matrix, we came to the decision that we will go with AISI M41 steel, as it exceeds both the compressive strength value and the average hardness value that we're looking for, and for lower cost than the other steel that we're looking at.
Proper heat treatment is crucial to the success of high-speed tool steels. The heat treatment process can be divided into 4 main parts, which consist of preheating, austenitizing, quenching, and tempering. The following diagram plots time versus temperature, illustrating the sequences required to properly heat treat high-speed tool steels. The first part is preheating. The preheating duration is of little importance as long as the part is heated throughout its cross-section. M41 steels can be preheated at 788 degrees Celsius. The second step is austenitizing, or hardening. High-speed tool steels depend upon the dissolving of multiple complex alloy carbides during austenitizing to develop their properties. M41 steels are rapidly heated to 1232 degrees Celsius for 2 to 5 minutes. The next step is quenching. The quenching or cooling of the workpiece from the austenitizing temperature is designed to transform the austenite that forms at the high temperature to a hard martensitic structure. M41 steels must be annealed at 871 to 899 degrees Celsius, followed by slow furnace cooling at less than 4 degrees Celsius per hour. M41 steels are then quenched by a salt bath of approximately 540 to 595 degrees Celsius for less than a minute, and then air cooled to room temperature. The following diagram shows a time temperature transformation graph for M2 high-speed tool steels that was annealed prior to quenching. Austenitizing temperature was 1230 degrees Celsius, which is very similar to M41 steel. It can be seen that the salt quench takes just under a minute to reach a temperature of 540 to 595, which is followed by air cooling for over an hour to reach room temperature. The last step is tempering. Following austenitizing and quenching, the steel is in a highly stressed state and therefore is very susceptible to cracking. The tempering process can be carried out in the range of 538 to 593 degrees Celsius, for about 1 hour. This should be repeated 2 times for the triple tempering effect. In the figure, you can see that the largest value of hardness is obtained by having a tempering temperature of approximately 530 to 570 degrees Celsius.
Time for this.